All right, section 6.3 is about disproofs and algebraic proofs. So we have two things to talk about. It's going to be a relatively short section. Number one is disproving things. And we're going to just talk about a little bit with the aid of an example of how we want to how we want to engage with something that we think we might need to disprove. And then we're going to look at a couple, 3 or 4 algebraic proofs. Where primarily we're using algebra to prove things with sets. So there's no new properties or anything that we need to write out. Everything in this section is going to be examples. So let's say we encounter a problem that says prove or disprove. All right, we talked a little bit about this in previous sections, but these are very hard questions because they ask us to understand the property. So the property that we are being asked to look at is for all sets A, B, and C, A minus B union B minus C equals A minus C. So, as we talked about before, when you have to decide whether you're going to prove or disprove, you want to make sure you know what's happening in the property or in the statement that you're looking at. So in this case, we need to know what these sets look like. So this first set, A minus B, well, this is the set of all of our elements A that are in A, and those same A's are not in B. And our B minus C set is the set of all little B elements that are in set B, and at the same time, B is not in C. And we're unioning these two sets together. So now the question is, can an A that's in A and that same little A not be in B, and because it's a union, or that B in B and B, that same little B not in C, can this be equal to an element in A that is not in C? That's what we have to ask ourselves. So if we are in this category or we're in this category, is that the same as being in this category? And the easiest way, just like we did before when we're looking at these things, is you can set up a Venn diagram. So let's say, because we're doing set difference and we're doing unions, we want to think of intersections. So we're going to have 3 intersections here. A, B, and C. And this is going to be our first side of our equal sign, and over here we'll have A, B, and C. A, B, and C. So this sign said everything that's in A that's not in B. So that's all this stuff. It's not going to be any of this, and it also includes the overlap that could happen with C. And then the other set of stuff is all the elements of B that are in B and not in C. So it's not going to include any of this stuff, but it is going to include the overlap in A as well as everything else in B. So over here we have everything that's in A and not in C. So that's this stuff, as well as everything that's in A. So the question is, can these two sets of Venn diagrams, can we ever change them around so that they have the same things? And the answer here is a big fat no. And the reason is, on this side, we have a bunch of elements that come from B. But on this side, our primary starting place is just A. Now, if we had a secondary clause that said that B is a subset of A, well, then maybe this could work. But as it sits, because of these elements in B, the answer here is no. So now we need to come up with a counterexample. And you can come up with anything, but basically what we need is we need B minus C, this set, to have things that are not in A minus B. In other words, our B needs to have some set of terms that are not in A, and also terms that are not in C. So I've come up with this combination of sets. So let's say we have the sets 1, 2, and 3 for A. B will be 2, 3, and 4. And C will just be 3 and 4. So now A minus C is 1 and 2, or yeah, A minus C is 1 and 2. A minus B is 1 and 4. No, not 4. 4 is not in 3, or in A. So A minus B is just 1. And then B minus C is just 2. So if we set up the union now, I've built these in a way that shows you the case where this is true. And notice that's because B minus C is a subset of A minus C, and A minus B is a subset of A minus C. So if we were to union these together, we would have the equality. So that means that B needs to have something that's not in A and not in C. So let's stick a 5 in here. So let's say 5 is a part of B. So then B minus C becomes 2, 5. So now when I union up A minus B and B minus C, we'll have the set 1, 2, 5, which is not equal to the set 1, 2. So a lot of times my advice to students in these types of cases where you're trying to disprove something in this chapter is come up with a set or a series of sets that actually works. Right? That's what I did first. 1, 2, 3, 2, 3, 4, 3, 4. When I set those up, I found one that works. And then look at how you can break it. So if the Venn diagram thing isn't really working for you, see if you can come up with an example that works like I did initially, and then break it. Once you know how to break it, you just need something else that's in this case we needed something in B that wasn't in A and C, and you can break it that way. Now if you can't think of any way to break it, that's your hint that, hey, maybe I should try and prove this. But these are, like we talked about, disproving things are hard because we have to decide that no, it's not going to work. So let's go ahead and look at some algebraic proofs with sets. So we are going to prove for n greater than or equal to 0 if set x has n elements. And the power set of x has 2 to the n elements. So when you encounter a proof like this, when you're looking at these sets, you can think of what you're dealing with. So this is the only information we have. So we have a certain set of a certain size, and we say that the number of subsets you can create then is 2 to the n. And so if you're looking at this, this has nothing to do with our set identities, none of our properties that we've seen. So this is going to be algebraic. And for this one, in fact, we're going to use induction. So we're going to let P of n, not a script P, be the statement. If x is a set with n elements, and P of x, the power set, has 2 to the n elements. Excuse me. And this is, of course, for n greater than or equal to 0. So, induction proofs, we need a base case. Our base case will be when n is 0. Well, if n is 0, then x is the empty set. And as we proved in the last section, the empty set's unique. There's no other empty set. And so the power set of x is the power set of the empty set. So all the subsets, and the only subset of the empty set is itself. Well, there is 1, which is 2 to the 0. So we've got our base case. Our inductive step now. We're going to assume P of k, not a script P, is true. That is, if x has k elements, and the power set of x has 2 to the k elements. So now we're going to try and see what this means for our k plus 1 case. So we're going to let y be a set of k plus 1 elements. Then we're going to let z be an element of y. So what we're going to do here, and the reason we're doing this example is to show a technique like this. So now we can partition y into y minus the singleton z. So why would we want to do that? Well, oh, I didn't finish this. This is union the singleton z. So you take y You take away z and you union that with z. So this whole thing, this union is equal to y, but we do this because this set, y minus singleton z, has k elements now. And therefore, the power set of y minus the singleton z has 2 to the k elements. So what we have to do is think about how do we then form the power set of our y, of our union. We know our union is one more element onto this. So we can take each of these. So every, I don't need to start down there. Every one of the elements in the power set of y minus z can be paired up with a subset of y that contains z. So for example, if we let w be a subset of y minus z and r be a subset of y, then w will equal r minus the singleton z. So we pair every single subset up with this, where the subset that we choose is only missing the subset from, or the only missing z from the subsets in y. Now, as it turns out, we have our w and our r. They form a nice little link that gives us every subset of y except 2. So these pairings account for all subsets of y except 2. And what we want to do is think about what those 2 are. So essentially what we're doing is finding subsets of r that are subsets of y minus z with z tacked on. So if you start thinking about all the subsets that could appear here, all your possibilities for w, there are 2 things that w can never be. Or there's one thing that w can be, and there's one thing that r can be that won't come from this. And so if you take r to be the empty set, you can't take away z, so that's not going to be here. But what you can find is the r that has the singleton set z, and then your empty set is the singleton set z, take away that singleton set. The other one you can't be, since w is a subset of y minus z, is y. Because w can't be it's a subset of y, but it can't be equal to y, because it's strictly smaller. It's taking away the z. So every single one of these corresponds to every single one of these minus 2. And since this corresponds to 2 subsets, if we link them up this way, we end up with the power set of y equals the power set of y minus the singleton set z union the singleton set z, which has 2 to the k times 2 subsets, which is 2 to the k plus 1. Oops. So the idea here is the reason that this corresponds to 2, every single subset here links to 2, is because w, while it equals r minus z, that gives you one subset, and then the original w also gives you another subset. So even though w is always going to miss z, the r that it links to gives you the other z. So even though we're missing those two, the empty set in w and the whole set y, those are contained in r. So the empty set r, well, the empty set is a subset, and then the whole set y, that's a subset here, and that's going to be linked to the whole set y minus z. So if you think about w and r, these account for all of the subsets in pairs. So you take a w, you take its corresponding r. You take the next w, you take its corresponding r. And you do the next one, the next one. Eventually you'll get to this set and this set. So every single one of these grouped together, it accounts for all. Why did I say 2? It's not all subsets of y except 2. It's all sets of y in pairs of 2. And so that's why we can say that we have 2 to the k plus 1. Because each of these that we pick that have this relationship, this is a subset of y, and this is a subset of y. And the way that we've defined this gets us the empty set that r cannot be, and the whole set y that w can never be. They get linked, these two. So every pairing you pick takes 2. And you'll get all possible pairs when you do that. So, by mathematical induction, P of n is true. For all n greater than or equal to 0. So the big thing here is when you're using induction, when you're using induction and you're using these algebraic proofs, you want to know that you can make these partitions. You can always partition a set by subtracting away 1 or 2 elements, or more if you need to. And that's going to be a useful trick, partitioning sets this way. So this was a fun little proof. Might be stretching the idea of fun there. But our next couple are true algebra proofs. So we are going to prove that A union B minus C equals A minus C union B minus C algebraically. I don't have enough space for algebraically. Algebraically. 2 L's? Yeah, we'll go with 2 L's. So the idea here is to give us another way to show set equality without having to do the element method, and showing that we have a subset of one and the other one's a subset of the first. So the idea here is we're going to be using all kinds of set identities. So A union B minus C. So the way that these work kind of like the trig identities that you proved back in pre-calculus. You pick one side and you work it up until you get to the other side. So this is set difference. So set difference is A union B intersected with C complement. And over here, we're just going to write set difference as our justification, because that's what it is. It's all the elements that are in A union B, take away the elements that are in C. So the only thing that's left would be the stuff that's in A union B and not in C. Well, then we can rewrite this as C complement intersect A union B. This is commutativity, or our commutative property. And now we can distribute the intersection. And we have C complement intersect A union C complement intersect B. And this is our distributive property. Distributive, ran out of space there, property. And now we're just going to rewrite as A intersect C complement union B intersect C complement. This is just commutativity again. And then this, going back up to here, is just our definition of set difference. So this is A minus C union B minus C. And this is set difference again. And we have our result. So not every single proof can be done algebraically. Not every single one is going to be easy to do algebraically. So there are going to be times where you just want to use the element method and show that you have subsets and containments in both directions. But I've got another one here you can try out. So prove that A minus A intersect B equals A minus B. So try this, pause the video here. Try and do this algebraically. So you're going to be using things like set difference, all our properties, distributive property, commutative property, associative property, all those identities, all those properties. De Morgan's law is good here. Did I miss any? I don't think so. I'll start you out here. So the first thing I would do, starting from the left, is use set difference. A minus A intersect B is A intersect with A intersect B complement. And this is set difference. So if you haven't paused it yet, do it now. Continue on your own. See if you get the same result. So De Morgan's law for sets is all about complements. And I realize now, did I skip it? I must have skipped that in the last section. So we'll write it out in a second here. But it's all about complements. So De Morgan's law for sets says that the complement of an intersection is equal to A complement union B complement. So this is De Morgan's law. Well, now we can distribute the intersection, and we have A intersect A complement union A intersect B complement. This is just distribution, or the distributive property. And A intersect A complement, well, that's just the empty set. And this will be union A intersect B complement. So this is just our complement laws. Complements tell us if you intersect the complements, it's empty. And then this is A intersect B complement. This is our identity. And A intersect B complement is nothing more than A minus B. Back to set difference. That's our result. So let's write out De Morgan's law for sets down here. For sets, I must have just skipped it in the last section for whatever reason. But it's A intersect B complement is equal to A complement union B complement. I forget which page it's on the book. It's probably in 6.2 now that I think about it, but there is the other version as well. A union B complement would be A complement intersect B complement. But that is a good law to know. We have some algebraic proofs, and that's the end of 6.3.